I would like to welcome you to this morning's talk, and we will start with a talk by John Simon on topological cavity QED and making materials from light. Please.
So it's a pleasure to be here. Make sure all my doodads and toys work. Yeah, okay, they seem to. As Tillman said, I'm going to tell you about ongoing work in my group making, in particular today, topological materials out of light. So, you know, the paradigm that we're most familiar with here is synthetic materials made from, I'm getting a call, sorry, either in the solid state, you know, electrons tunneling around in some topological ionic lattice, or ultra-cold atoms hopping around in some optical potential. And then this is, of course, also where I come from. And so the question to ask, really, in my mind, is why change gears and try to make materials out of photons? And to me, there are a number of really wonderful answers to this question, both about the sort of control that we get of our photons in the single particle sector, and the kinds of probes that we get of the states that we make, and finally, with the addition of strong interparticle interactions, with the sorts of tools that we have for building many-body states at the end. So this last bit is sort of directional rather than experiments that we've already performed, but I kind of feel like with this audience in particular, this question of how to really build these many-body states is a rather pertinent one. So with that in mind, I'm going to talk about kind of two experimental efforts that are ongoing. The first entirely in my group, and the second in collaboration with Dave Schuster's group, building photonic materials in two different systems. You can think of them, I guess, as sort of the rubidium and lithium of the photonic world. That is to say, qualitatively, they're both photons, but the sorts of science that we have the ability to explore in the two systems are actually sort of rather different. So this first system is going to be trapping optical photons in non-planar resonators, and this is going to give us access to sort of Landau level physics of photons, in fact, on conical geometries. So we'll explore when Z kind of physics, this interplay of magnetic fields and curvature, and ultimately talk about some ideas for building many-body states, particle by actually implementing some flux threading schemes. And the second set of experiments, which we'll talk about time permitting, are based upon RF and microwave photons in lattices rather than in bulk. And in these systems, we've been able to realize both Z2 and sort of Chern insulators, where we use ferrites to break time reversal. And so the outlook there is to add these transmons to make the photons interact with each other, and then engineer chemical potentials based on some ideas from Mohammed and others to really make these photons sort of thermalize into many-body states. So with no further ado, let's talk about making photonic materials in the bulk from optical photons. So the basic idea of these experiments is to take the Hamiltonian engineering ideas that one gets from exciton-polariton or photon BEC experiments, where the photons are trapped in optical resonators, and combine this with the strong interactions that one achieves by coupling photons to Rydberg atoms, so these Rydberg EIT experiments from Vladen and Misha and others. So essentially, to prepare an optical resonator, a multi-mode optical resonator, so that our photons have kinetic degrees of freedom, and couple them to a thin Rydberg-dressed atomic ensemble. But before we get into technical details of any of this, I'd just like to explain this central premise, which is that photons in multi-mode resonators actually behave as massive particles in harmonic traps. and it's really essential to understand this before we move forward. So I want to emphasize, for starters, that I'm talking about a real space analogy, not a Fock space analogy. By which I mean, if I say photons in a resonator look like a harmonic trap, you immediately think 0 photon, 1 photon, 2 photons, 3, 4, 5. That's not what I mean. What I mean is that in real space, in the resonator, a single photon can be in a lowest harmonic oscillator mode, or a first excited mode, or a second excited mode. So let's explore this in a little bit more of a ray optics limit first, just to get a sense of what I mean. If I inject light off-center between these two mirrors, what I claim will happen is that the wave packet will oscillate back and forth in this transverse plane, just like a massive particle in a harmonic trap. Okay? You can understand this very easily with rays. I'm not sure if it's clear. Basically, there are rays bouncing back and forth inside this cavity. And what I'm just doing is coarse graining. I'm looking only in the central cavity plane. So those of you who are particularly perceptive will notice immediately this is a Floquet kind of a story that we're going to be telling. But what you can see is that this wave packet does oscillate like a massive particle in a harmonic trap. And in fact, we can then go to a wave picture and see that this is actually formally a good correspondence. A massive particle in a harmonic trap has these Hermite-Gauss eigenstates that are uniformly spaced in energy. And anyone who has ever played with laser resonators knows that the eigenmodes for a particular number of wavelengths longitudinally in the cavity are these Hermite-Gauss modes that are, again, uniformly spaced in frequency. So as long as we think of a particular longitudinal quantum number, these photons behave like massive harmonically trapped particles. Okay? So just to really belabor the point, if I put a photon in off-center in my harmonic trap, I can write that as a superposition of the lowest state and the first excited state of the harmonic trap, or for the photon of the TEM00 mode and the TEM01 mode of the resonator. The TEM01 mode accrues some phase relative to the lowest mode, so sometime later they'll be out of phase, and this will put the photon on the left side of the trap. So this is freshman physics, but my only point is that it applies equally well to photons trapped in optical resonators as it does to cold atoms in lattices or baseballs or anything else. Okay, so the picture you should have in your mind, if these are our two resonator mirrors at the top and the bottom. Yes?
Okay, so where does the mass come in? Like, you're controlling the system through, I guess, the shape of the cavity and stuff, so you should have a frequency and a mass. Where are those coming from?
It's a little funny. I can give you a formal answer, which is that the trapping frequency is the transverse mode frequency spacing of your resonator, okay? And the mass actually comes from the width of the TEM00 mode, right? You can think of that as sort of the 0-point motion of the particle in the trap, and from that you can back out a mass. That's sort of backwards, right? But the statement is you can only talk about a photon mass once you think of this as sort of photons rather than waves. But it all fits in the Floquet picture, yeah.
Just the quadratic dispersion in the transverse direction.
It's not quite that in a cavity. You have to really do the Floquet story to get the right mass in the cavity. We'll talk about that a little more in a moment. I just want to give you guys a physical picture to have in your mind first, which is if I've got two mirrors and I've got my light bouncing back and forth really fast longitudinally, the photon is sort of delocalized. It's in a single longitudinal mode, and that longitudinal mode oscillates back and forth transversely. Okay, so we have a good separation of timescales here. Okay? And again, you can compute what this mass ought to be, and it's some fraction of an electron mass. For those of you who are interested in sort of understanding this a little bit more formally, the basic picture is if I have some electric field distribution in this initial plane of my cavity, okay, I can compute how it propagates to the final plane of the cavity before the second mirror, it's just e to the I kz times the length times this initial field. But the point is that kz is actually dependent on the transverse momentum, right? And so what this means is that the field at this second plane of the cavity is the field at the initial plane times e to the I alpha p squared, where this is this transverse momentum p, okay? And then when we reflect off of the mirror, we get a phase that depends upon this transverse position x, okay? And then we propagate back, get a phase that depends on p squared, hit the second mirror, get a phase that depends on x. So the field after a round trip is then given by e to the I h flow k times the round trip time times this initial field, where the flow k Hamiltonian is given by this terrible mess. But it turns out you can play Baker-Campbell-Hausdorff kinds of games if that's your thing, and show that this really corresponds to just a quadratic Hamiltonian at the end of the day. Okay, so I hope I've convinced you at this point that we can make our photons look like massive harmonically trapped particles just by putting them in these resonators. The challenge is, can we add a synthetic magnetic field to this story? Okay, because this is a topological physics conference. I guess you know the answer is yes. But to understand that, we should think about World War I and World War II submarine movies. Okay, you see these seriously. So you see the U-boat captains, right? And they've got their periscopes. And did you ever wonder why, when you're looking through your periscope, the captain has to go like this? Why isn't there just a little crank?
Upside down.
What?
If you cranked it, you would turn upside down.
Exactly. But the upside down isn't the worst. In between, the image rotates, right? And this is the key point. Thanks for spoiling it. So it was obvious to one person. So the basic idea then is this. Imagine I have my periscope, okay, with two mirrors. So I've got my, and this is going to be my image. It goes in, comes up, comes out, okay? So it went from here to there, it got inverted. If I instead had a periscope like this, it goes in, goes up, comes out, didn't get inverted. But if it goes at 90 degrees, I get a 90-degree image rotation, okay? And so what you can kind of see is that if I have two mirrors like that, and then use my last two mirrors of my cavity just to close it, to bring the beam path back on itself, I have engineered a cavity where I have a mass term and a harmonic confinement term, but on top of that, I've turned the lab frame effectively into a rotating frame, because on every round trip I get a little bit of rotation. Yes? Okay, so qualitatively you can draw a picture like this. This is following a ray parallel to the cavity axis for flat mirrors around the cavity many times, and you can see that it just kind of precesses around the axis. And then you have to add the mirror curvature on top of that, because remember, this corresponds to a combination of centripetal terms and Coriolis terms. And to get just a magnetic field, we only want the Coriolis term, right? So we're going to have to add mirror curvature to cancel out the centripetal term, and that'll leave us with our photon in a Landau level. So how does this look in a wave picture? One can draw the modes of the cavity when it's planar, and they look just like a massive harmonically trapped particle. You've got the lowest state of your harmonic oscillator, 2 first excited states, 3 second excited states, and so forth. What you're going to find is that as I twist the cavity, on every round trip, each of these guys has to rotate a little bit, right? So that says that these two can't possibly be eigenstates of my cavity, right? The eigenstates have to be superpositions of these two, this one plus or minus I times that one. And the one that rotates in the same direction as the cavity twist is going to go down in energy and the one that rotates against the cavity twist will go up in energy. Okay? So I'm just going to show this same animation again, but I'm going to allow these eigenstates to change and move in energy. And so what you see if you just do this numerically is that you should begin to approach this situation where we have L equals 0, 1, 2, 3, 4, so forth, Laguerre-Gauss modes, which are basically the states of the lowest Landau level in a symmetric gauge. Okay? Now, if you're looking closely, you can see that these guys are distorted, right? And I didn't go quite to the degeneracy point. And it turns out that this problem is exactly the same one that one runs into with cold atoms. Okay? If you start rotating a trap, when you expect to get just to the Landau level configuration, your trap explodes. And so why does this happen? Imagine that you have a slightly sort of astigmatic trap. The X and Y trap frequencies are slightly different. Okay? And in fact, to spin the gas up, I have to have a trap where the two axes have slightly different trap frequencies, as Bert pointed out yesterday. Otherwise, rotating the trap doesn't do anything, right? But the basic point is that I don't approach the Landau level configuration until the rotational frequency of this trap approaches the trapping frequency. And when that happens, I'll cancel out one of these two axes before I cancel out the other, okay? And that'll leave me with some kind of a hyperbolic trap, okay? And this hyperbolic trap, basically, at every state is now an edge state that gets guided out to infinity. And so you can think of this as why cold atoms basically become unstable when you reach this sort of Landau level degeneracy point. You're unstable, that is, to L equals 2 disorder in your trap. And our cavity mirrors are a little bit, well, we're hitting them off axis, basically. You have to make this twisted geometry, and that drives these delta L equals 2 transitions, just like you have for cold atoms. Okay? So, why have I belabored this technical point so heavily? Because what we're going to engineer now is a cavity where you can't drive delta L equals 2 transitions. We're going to make something that looks like a lowest Landau level, okay? But it only has L equals 0, 3, 6, 9, 12, so forth, okay? So how do we do that? Well, let's draw a bunch of different Floquet manifolds, also known as longitudinal modes of the cavity, okay? And I'm just going to draw the lowest Landau level qualitatively for each one, okay? And then what we're going to do is just keep twisting the cavity beyond the point where I get these lowest Landau levels. And what you see is if I add just the right amount of additional twist, I can bring this L equals 3 state from the next longitudinal mode into degeneracy with the L equals 0 mode, okay? And L equals 6, 9, 12, 15, so forth. And you can't see it at all on the projector. I've also brought L equals 1, 4, 7 into degeneracy, and 2, 5, and 8. And we'll come back to those in a little bit. So, okay, so this is our new stable lowest Landau level. But of course, it only has L equals 0, 3, 6, 9, 12. So what is this object physically? So I'll give you a hint. Let's just trace a ray around a cavity like that. Okay, and you get these cyclotron orbits, just like you expect, okay, but you get 3 copies of them. First, on one round trip, it goes sort of around, and then it comes back on the next copy. Then it comes back on the next copy, and then it returns to the first one. So what is that object physically? Well, we chatted with Paul Wigman and Damson, and what we finally realized is that this corresponds to the photons living on a cone. So how can we understand that? Well, first, let's take a conical surface, okay? And what you'll notice is that, do I have a sheet of paper? A cone is everywhere flat except at its apex. And by that I mean that a sheet of paper is flat and I can wrap it into a cone without having to crinkle the paper anywhere, right? The only point of curvature is at the tip, okay? Everywhere else, space is flat. And in fact, the cone that I've chosen happens to be a third of the plane. So you can think of dynamics on this cone as dynamics in the plane with the added requirement that when I go off this edge, I have to come back on the other edge, okay? And so this is sort of this 3 copies that I was mentioning a moment ago. And how do we make this experimentally? Well, we take these sort of 3D drawings and we 3D print them. Usually I bring one, but unfortunately I just switched backpacks. It's just a little plastic structure into which we stuff super polished mirrors. And when you get the length of this structure right to within a micron or so, you get these crazy 3-fold kind of degenerate structures, these cyclotron orbits I mentioned, or the galaxy, or what have you. So the question then is, how does one demonstrate that this is the lowest Landau level, or the first Landau level, or what have you, on a cone? And so one of the things that I think is actually most exciting about these photonic systems is that we have a sort of orthogonal set of tools for exploring the single particle band structure or dispersion from what exists in cold atoms. So I'll just tell you how we make these kinds of measurements. The basic game is to just do spectroscopy of the single particle eigenstates, okay? As we vary the resonator length, which sort of changes a combination of the twist and the harmonic confinement, okay? And what you see is we have L equals 0, 3, 6, 9, and we can just image these modes with a camera, okay? And as we vary the resonator length, they come into degeneracy at this point. And then we have all these other sort of sets of modes that also come into degeneracy. If we zoom in here, I'm claiming that's our lowest Landau level, okay? So you can look at these eigenstates, 0, 3, 6, 9, 12, 15, 18, 21, go quite a ways up, and they all come into degeneracy to within about 1 megahertz as you tune through this length, well, the length where they become degenerate. And the thing that you would worry is that as you tune through this degenerate length, either there would be some avoided crossing from disorder, or the cavity finesse would go to 0, indicating that the photons are kicked off to infinity, and neither of those things seems to be the case. It seems, as we hoped, that the system is in fact stable at that point. And so what I'm plotting here is these sort of Fock-Darwin eigenstates at different detunings from degeneracy. And when we tune right onto degeneracy, what you can see is that there's a little bit of disorder. We think it's a cut in the mirror that's about an angstrom deep that guides the photons out a little bit, and then they come back in. So you can think of this as kind of an edge state on the cone. So again, you can say we've got these eigenstates. Does that really indicate that it's this Landau level on a cone? So we can explore this in a sort of more physical way by exciting the system at the cone tip and then saying, well, if this is really a Landau level on a cone up to some gauge transformation, it should be translationally invariant, right? So I should be able to excite this lowest state away from the cone tip. So let's just translate it and excite again. And indeed, I can excite this state away from the cone tip. I just get 3 copies. And I should now be able to excite an L equals 1 state, not an L equals 3 state, but an L equals 1 state about this new kind of guiding center. And indeed, I can do that as long as these orbits don't enclose the cone tip. What happens when they do enclose the cone tip? Well, this high angular momentum, I think it's like 25 orbit, interferes with itself, okay? So now you might ask yourself, is this a feature of the cone, or is this just a feature of this bizarre way that we've implemented it with the cavity, okay? And the answer I'd like to convince you is that it's actually a feature of the cone. So the way to think about this, here we have an even larger orbit, okay? And it looks like it just encircles this cone tip once, right? But if I take a third of the plane and unwind this, what you can see is that it actually encircles the tip 3 times, right? You can kind of see why here. We've got this flat space cyclotron orbit, and I'm just going to move it towards the cone tip as though space is flat everywhere. And what you see is that once it goes over the cone tip, it encircles it 3 times, right up until you hit this point where it looks like it just encircles it once, right? But with a smaller circumference. So this, to me, is actually a really fascinating thing. So the area enclosed by this orbit has gone down, right? So what that means is that effectively the density of states has gone up at the cone tip compared to everywhere else in the system. And you can understand this. This is sort of a naive classical depiction of a lowest Landau level with a bunch of little cyclotron orbits. I'm going to cut out a third of the plane and just wrap it on itself. And what you can see is that this orbit at the tip has a smaller area than the other ones. Okay? And this was actually predicted in the early 90s by Wen and Xi. The basic statement is that the local density of states in a Hall system depends both on your magnetic field and on the local spatial curvature. Okay? But this spatial curvature term is always very difficult to tease out, because if you try to have a small amount of spatial curvature, this term gets washed out in disorder and other kinds of effects. And if you try to have a very large amount of curvature on the order of your magnetic length of nanometers, then essentially what you find is that bond distortions change your chemical potential by more than this effect. So it's very hard to see this physics. But we can actually just do it. And what we do is we tune just a little bit away from degeneracy so that the eigenstates of our system are split out. And we measure their sort of probability distributions individually, normalize them, and sum them up. And what you see is that for this cone with L equals 0, 3, 6, 9, and so forth, you get an excess density right at the tip of the cone. If you play this same game for the cone that starts with L equals 1, remember I mentioned there's another degeneracy that starts with this L equals 1 state, then you get what looks like a dip at the center. Okay? And you can again play it for the cone that starts with the L equals 2 state, and you get an even larger dip. Okay? So we can now sort of normalize to the density of states away from the tip and compute how much excess state density there is here. And it's a third of a state. And this guy is missing a third of a state. This one looks like he's missing a little bit. But remember, before we integrate up, you have to multiply by the radius, right? And so the little excess density here turns out to cancel that. Yes?
Can you tune between these manifolds in the same cavity, or you have to
So they're all degenerate at the same time. They're just different in energy by a few gigahertz. Just a laser frequency, exactly. And we're going to actually talk about transferring, an idea for transferring photons from one cone to the next as a way of flux threading. Because the basic point is the difference in density of states at the cone tip actually comes from a third or 2/3 of a flux quantum actually threaded through that tip. Okay? So if you could take a state that lived on this cone and adiabatically transfer it from one to the next and back to the first, that would correspond to threading a unit of flux through the system. Okay? So one can extract from these numbers the mean orbital spin, and I think much of this physics becomes more fascinating once you start trying to do it in a fractional Hall regime, but as a proof of principle, this agrees pretty well with the 1/2 that we expect for an integer quantum Hall kind of state. Okay, so imagine that one could add interactions in this picture. and I'm going to tell you about our progress towards doing that, but the question is, how should you even think about that? You want to have a two-mirror cavity, just for simplicity here, and you think of your polariton as having real space, or the effective flow k-plane, somewhere in the cavity, okay? One can then say, away from that plane, you move towards Fourier space, or away from that plane, the light diffracts, whatever way you like to say it. But what I want to do is add a medium that mediates interactions between the photons in that plane, and that'll give us sort of real space interactions. So we now have a planar cavity under vacuum, sort of a 0D quantum dot analog of this system, into which we transport an atomic ensemble of rubidium atoms that we slice down to about 20 microns of thickness. And we've now observed strong light-matter coupling and this Rydberg polariton resonance. So the next step is to add these interactions by going to higher Rydberg states. But then the question is this. Great, we demonstrate that we have an interacting system. Yeah, great. How do we make some kind of an interesting many-body ground state for this system? And I want to suggest two different approaches. The first is, imagine just injecting photons first into this L equals 0 mode of the cavity. In an interacting regime, I can put one photon into the L equals 0 mode, but sort of photon-photon interactions prevent me from putting a second one in. Okay? But if I try to put two photons into this L equals 1 mode, they can collide and go to 0 and 2. And it turns out that a particular superposition of those two states has no interaction energy, and that's called a bosonic Laughlin state. Okay? And so I can inject two photons into this L equals 1 mode before I get a blockade, and what will come out the other side is a photonic Laughlin state. If I inject on L equals 3, or L equals 2 rather, I'll be able to inject up to 3 photons before I get a blockade and so forth. Anyway, there's a paper from Mohammed that says that this is a terrible idea. It works up to 2 or 3 photons, but the basic point is that the matrix element overlap between n photons in this state and the n particle Laughlin state falls off either exponentially or super exponentially in the number of photons, right? So it's just a very bad way to do it. What's a nicer way, we think, is to inject a photon into the cone tip and then thread 2 fluxes through the system by performing sort of a photon, an upside-down Raman transition to transfer the photon from the L equals 0, from this unthreaded cone to the once-threaded cone to the twice-threaded cone and back. And that puts 1 flux in. So if you do that twice, you've essentially put 2 quasi-holes into your system. And that state has good overlap with the 2-photon Laughlin state if I just inject another particle at the cone tip. So you can think of it, what I'm going to plot actually is the root Jack polynomial as we do this flux threading. So the photon moves out the cone, and then we inject another guy there. We go out twice, inject another one. And what you discover is that at every step you have about a 50% overlap with this n-photon Laughlin state, even as you thread more and more fluxes through the system. So it looks like this is kind of a linear scaling as opposed to an exponentially bad scaling for making the states. So there were 2 other topics I wanted to talk about, but I think instead I will give you the very short version of this story, which is just to say that we've succeeded in making these room temperature topological circuits that act like sort of Z2 topological insulators. We see edge states that propagate around the edge of this kind of a system where, hello, there we go. Yeah, so we can see these edge states propagate around the edge. This is real data. We can watch this in time. If we excite both spin states, you can see it acts like a spin filter and sends them in opposite directions. But we wanted to take these ideas, again, into a strongly interacting regime. And so what we've made is a superconducting time reversal broken analog of this that actually has a lot in common with John Giannopoulos' ideas and experiments, where basically this is one magnetic unit cell, and it has this yttrium iron garnet crystal in it that breaks time reversal symmetry and gives us these Hofstadter bands. And so, again, in this system, we can see nice edge states, and the next step is to add transmon qubits to mediate interactions between the photons. But the question you again ask is, how do I build a many-body state if I have a strongly interacting Hamiltonian? And this, again, I think is a wonderful place where photons really shine. And the statement is, let's couple this thing to a reservoir of particles that can tunnel in and fill up our Chern insulator. So we're going to have some kind of autonomously stabilized little subsystem here that always stays with one photon in it. So even once one tunnels into this system, it'll replenish itself. And it turns out you can do this by basically coupling a harmonic oscillator, a lossy harmonic oscillator to an anharmonic oscillator and driving it. You can generate this kind of an inversion. And so anyway, I think it's a very exciting time for having a very different approach to starting to build up few body kind of topological states. So this is our microscope for a 4x3 lattice at the base of our dilution refrigerator. And this is the graduate student who got to do all the wiring, Clay. Actually, I don't know. Did he do it all, or did you do it, Alex? No comment. So anyway, I think with that, I'll conclude and thank you guys, and particularly thank my group. I did want to kind of highlight these three guys. I guess most of you probably know Alex, who's been sort of spearheading this lattice microwave materials and the chemical potential effort, and Ariel, who's been working tirelessly on these bulk polaritonic materials, and my graduate student Nathan has really, along with Ariel, taken the lead on these twisted cavities that we're now combining with the polaritons. So with that, thank you.
Thanks very much. Questions?
Now, if you can controllably dial in the total angular momentum, you don't really need to make a degeneracy. You can have these fractional quantum Hall states if you can engineer the interactions, even without this degeneracy, as long as angular momentum is conserved on the time scale of your experiments.
So I think the challenge, so Jacopo has a paper on some of this stuff for photons, and the challenge is that it's very hard to mediate broadband interactions for photons, for one thing, and the other thing is there's always some disorder in the system that breaks this sort of forward-backward symmetry, and so you get scattering into all of the other states in practice. But I agree with you that fundamentally there's nothing that prevents you from just making a very, very clean cavity with a broadband interaction, and then you'd be good.
So how does this cavity physically look like? How do you move this last mirror? Do you have to rebuild the cavity, or is there a clever way of doing it?
So it turns out basically it's just 4 mirrors, 2 mounted vertically and 2 mounted horizontally, and the beam kind of goes around like that, and you just change the length over a millimeter or so in this direction, and the beam moves around a little bit on the mirrors, but you know they have nice positive curvature, so it's confined. It works out okay.